Hey everyone, this is Mr. Hernandez with you today, and we're going to be working on inverse functions. So let's get right into our lesson and see how inverse functions work. So by the end of the day or end of this lesson, you're going to be able to answer these two questions. How do we find the inverse of a function? And then how do we determine if a function is one-to-one? Now, we're going to actually talk about the first one very, very quickly, and then we'll talk about the second one, and then we're going to go back into the first one and really dive into it. So some vocabulary words that you're going to need to know. Inverse. The inverse of f, so you're not going to say this as f negative 1, what you're going to say is the inverse of f. If you say f of negative 1, people are just going to look at you weird. The other way you could say this is f inverse. That's also okay. Very, very common. And then lastly, we're going to use the words one-to-one. You saw it on the last slide. And what that means is if the function has an inverse that is also a function, then the function is one-to-one. So let's look at this. What are inverse functions? Now, in class, I tell a story about my grandma getting lost and having to give her directions. But we're really just going to be looking at the tables right here. But a great way to think about functions is go back to this definition, and it is the undoing of an action. So thinking about directions, if you turn left and then you want to go back the way you came, you're going to end up turning right. So what are inverse functions? Let's look at f of x equal to x squared minus 4. We are going to create this table, x and f of x. So when x is, let's go negative 3, negative 2, negative 1, 0, 1, 2, and 3. So when x is negative 3. We're talking about that x. We're going to get 9 minus 4, which is 5. When x is negative 2, we're going to get 4 minus 4, which is 0. When x is negative 1, we're going to get 1 minus 4, which is negative 3. And then when x is 0, we'll get negative 4. This is a quadratic function translated down 4 times. So when we have x as 1, we're going to get negative 3. X is 2, we're going to get 0. And when x is 3, we're going to get 5. Notice here how they are just symmetry. Lots of symmetry happening today. So we're going to go negative 3, 1, 2, 3, 1, 2, 3, 4, 5. And then negative 2, 0, negative 1, 1, 2, 3, down 3. 0, negative 4, and then we have that symmetry that I was just talking about to create my favorite shape, a parabola. Okay, I know that's a little bit wonky, but you get the idea. This is a parabola. So now when we go over here to, actually this is supposed to say inverse of f of x. And it's actually not going to technically be the inverse, but we'll talk about it. We'll see what we get. So we are going to swap the domain and range. That's what we're looking at today. So my domain are the x values. My range are the y values. So I look at that table over there, and I'm going to swap them. So when I swap negative 3, 5, that's going to say 5, negative 3. And then 0, negative 2, and then negative 3, negative 1, negative 4, 0, negative 3, 1, 0, 2, and 5, 3. Hopefully I did not make a mistake there. So now we're going to graph that function, which is going to be the inverse of f. So 5 over 1, 2, 3, 4, 5, 1, 2, 3 down, 0, 2 down, negative 3, 1, 2, 3, 1 down, and then we are going from here, create a nice shape. If you're already getting ahead of me thinking about how this is not a function, you are correct. That's what I was just talking about. But we're going to add a couple more things here. Notice my domain of my original f of x. My domain, actually no, not the domain, we want the range. The range of this function is going to be negative 4 to infinity. And I want you to make the connection to what we get here on the domain for the inverse, we are going to get, for the domain, -4, infinity. So the range and the domain literally switch. If you're looking at your graph and you're like, oh, look at that, there's some symmetry happening there, you are correct. It is symmetrical across this line, y equal to x. So that line is y equal to x. And there is that morphing that's happening. We are saying here that the y is the same as the x. The x is the same as the y. The domain and the range swap. We're going to come back. So this is everything about inverse functions. You've seen it in a table. You've seen it in a graph now. And now we're going to go on to our next slide, where we talk about the horizontal line test and one-to-one. So for the horizontal line test and one-to-one, I want to graph these two functions first. So jumping onto our calculator, in my class we use the TI Inspires. There we go. Alright, so go to new document. Do you want to save the unsaved document? No. Say no to drugs. We're going to add a graph. We want to put in this fraction. So we're going to go 4 divided by, whoops, we already have the fraction 4. That's a lot. 1/4. There we go. Divided by x. There is our graph. All right. Now I want to drag this over onto our paper. So what the horizontal line test says for us is at any point, let me get a horizontal line up. At any point on this graph, does it cross the function more than once? So as I move this line across, you will notice it only touches it one time at any given y value. We have no sharing x's. We have an asymptote. This is 0. It's not crossing the line at all, but that's okay. We're just seeing if it touches it more than once. So this passes, f of x passes the horizontal line test. So the function is 1-to-1. That's what we're going to say. We know, using the horizontal line test, that the function does have an inverse function. That's what that says to us. Now we're going to graph g of x. Let's see. All right. So let's go back here. All right, so I just want to delete what I had. So press up, delete, delete. And I'm going to put in x squared plus 5x minus 7. Enter. And let's kind of move this down a little bit. And let me switch this up. Zoom standard. And let's just change the y value to, I don't know, let's go with -20. Maybe that'll work. Awesome. That is an excellent picture. So when I drag this on, we'll be able to talk about it using the horizontal line test. So again, using this horizontal, I'm just going to grab it from over here. Oh, there it is. And we're going to need to bring it forward. Apparently, it does not like this. All right, you send to the back. Goodbye. There it is. So notice here for the horizontal line test, I am touching the graph more than once. At any point that I can put this graph in, I'm going to touch it twice at several points. So the function is not 1-to-1. So actually we don't have f of x. We have g of x is not 1-to-1. because it does not pass the horizontal line test. And that's an abbreviation everyone's going to understand. So we know the function is not one-to-one, which means that this, the inverse of g of x, does not exist. We can't find one. Well, you're probably looking at me and saying, look, Mr. Hernandez, this problem was a parabola too. We got a function. Actually, this is not a function. That's what the horizontal line tells us. So remember from Algebra 1 and Algebra 2, actually that's not what I need, to tell us something is a function, you use the vertical line test. So as I'm coming across here, notice for the blue, for f of x, this is a function. It is passing the horizontal line test. But for the green, it's touching it twice, it's touching it twice, it's touching it twice. The green is not a function. So the horizontal line test helps us determine if the function has an inverse before we even start looking for an inverse. So that's why I said this notation over here for right here. That notation is actually not correct because it's actually not an inverse function. So f of x is not 1 to 1. So the horizontal line test is a very quick way to determine if a inverse function exists. And sure, we can graph an inverse, but that would be an inverse relation, not an inverse function. And you can see that it's not a function using the vertical line test as well. Well, that's great, but we actually haven't found any inverse functions. Well, that's where this comes in. So let's start with f of x equals 2x minus 4. Let's start by graphing the function. We're always going to start by graphing and using the horizontal line test. So let me pull my calculator up. New document. Say no to drugs. Add a graph. And we have 2x minus 4. All right. Does this function pass the horizontal line test? Well, it's just a line. So at any point, if I drew a horizontal line across here, it would continue to pass. So yes, it passes the horizontal line test. That is always your first step. So horizontal line test, check. The next thing that you're going to want to do, so you don't have to do work later on, go back to your function, go back to your graph, determine the range. Well, again, this is a linear function. I don't have any square roots or fractions happening here. So no variables in a denominator, so no rational expressions. So the range here is negative infinity to positive infinity. All right, so that'll help us out later. All right, so now we want to find the inverse of f of x. We have proven that an inverse will exist. So, okay, that's great. So in order to do this, we're going to start by switching f of x to y. Now, a lot of teachers will teach you to swap x and y and to like write this here as x equal to 2y minus 4. And honestly, I used to teach it like this. That's not the way I'm teaching it now because that's not the meaning of an inverse. We're not swapping the x and the y and then solving for y again. We are solving for x. We are solving for our actual domain. So let's go ahead and do that. If I want to solve for x, I'm going to add 4 to both sides and get 2x. And then from there, I'm going to divide by 2. So we'll get y plus 4 on 2 equal to x. So that itself is my inverse function. But when I write this using the correct notation, we're going to say the inverse of our function f, the inverse of f of x, is going to be x plus 4 over 2. So now we are saying the inverse is now a function of x, not of y, of x. So this x here is actually different. We're talking about different things. All right, and sometimes we're going to have to worry about domain restrictions. But this function, actually we will not need any domain restrictions because we figured out the range was negative infinity to positive infinity earlier. So let's go ahead and graph this just to take a look at how it looks. X plus 4. And we want to divide all that by 2. Actually, let me go forward. Whatever. This is going to work out. Y equals x plus 4 divided by 2. It's the same thing. So notice here, we have that nice symmetry along the line y equal to x. There is no restriction on my domain. The domain is negative infinity all the way to the right to positive infinity. Let's get rid of that. Now on to g of x. Again, we're going to work this the same way. So we need to figure out, does this pass the horizontal line test? So let's see. We're just going to go and graph it so that we can get some of the information that we need. So new document. Nope, that's not what I wanted to add. I wanted to add a graph. And we are going to have the square root of x plus 4. There it is. So does it pass the horizontal line test? Horizontal line, horizontal line. Yep, seems to only touch it once at any given point. So at no point does it pass it twice. So we are yes to the horizontal line test. And then also get your range. Your range here is 0 all the way up to positive infinity. So horizontal line test, check. And then our range is 0, comma, infinity. That's going to help us out later. Now we need to determine what is the inverse of g. So we'll switch this up to y. Square root of x minus 4. And the only reason we switch this up to y is because I think some people get confused on moving this entire thing around, the entire function around. So just switch it up to y. Alright, so we need to square both sides. So we get y squared equal to x minus 4, and then add 4. Y squared plus 4 gets us x. And then we can write this using the proper notation, except we're not using f. We are using g. The inverse of g is equal to x squared plus 4. Now there is a bit of a problem. If you look here and remember our definition, x squared plus 4. Here's the graph. You're going to notice, let me just move this up a little bit. Okay, you're going to notice that there are no negative values here on my range. So if we swap the domain and range, notice here how the domain does not seem to match up, does not seem to swap, because it's negative infinity over here to positive infinity. Well, what's happening? Well, if we were to write the inverse of this function, x squared plus 4, we would get what we saw earlier on that initial problem. The graph would dip below the x-axis, which means this wouldn't ever have been a function. So we need to restrict the domain of x squared plus 4. You see that range that we got earlier? 0 to infinity? We need to restrict the domain to 0 to positive infinity. So that's why we do that legwork early on. So my domain for this function is 0, comma, infinity. There it is. Again, so these are a good couple of examples. If you're not really understanding, go ahead, pause the video, come see me during tutoring, because I don't really want you to move on and continue to get confused, because we're just going to be finding inverses for the rest of this video. Finding an inverse algebraically. That's what we're going to be looking at here. Again, and it's going to be the same exact process. The horizontal line test. Does this pass? You're going to want to graph it. There we are. New document. Nope. Add graphs. We want the fraction x minus 1 for our rational expression, and x plus just one of those, 2. There it is. Does this pass the horizontal line test? Yes, it does. So we know an inverse function exists. Now we also want to get the range. We have this horizontal asymptote happening at 1. So we're going to want to take that out of our range. So we're going to say our range is negative infinity to 1 union 1 comma infinity. All right, now we're going to get this down. This one is going to be a bit of a long one. So if you need to use the bathroom, I would say go do that right now. So y equals x minus 1 on x plus 2. Our goal, again, is to solve for x. Solve for x. If you notice, though, I have 2 x values. So how do we get 1? Well, you're going to have to do a little bit of factoring here. So we're going to multiply both sides by x plus 2. So we're going to get yx plus 2y after distributing. And that's going to get us x minus 1 alone. So then what we have to do next is subtract x on both sides. So yx plus 2y minus x equals negative 1. You want to get all of your x values together, but if you notice this middle term here, that 2y, that has no x with it. So we have to boot it away. So subtracting 2y on both sides. So now we're sitting at yx minus x equal to negative 2y minus 1. And now you're going to want to factor out an x on the left side because they both have an x in common. So we'll get x times y minus 1 equal to negative 2y minus 1. Now I have, if you notice across the entire problem, I have only one x, and that's right there. That's perfect. We still need to solve for it, so we need to divide both sides by y minus 1. And we'll be good to go because those will divide out. We're going to get x equal to negative 2y minus 1 over y minus 1. Don't forget your function notation. The inverse of f of x is equal to negative 2y minus 1 over, sorry, not 2y because we switch this to a function of x, negative 2x minus 1 over x minus 1. And we do have a restriction on this domain because look, you cannot divide by 0. So if we have 1 in our denominator for x, then 1 minus 1 is 0 and we're dividing by 0. But if you look again up here at our range, it is taken out early. So we just write our domain for this function is only defined for negative infinity to 1 union 1 to infinity. So that's how you determine what the inverse function is when you have a rational function. Looking here on our next one, g of x equals 8 minus x cubed. So let's see this. We're going to check the horizontal line test. I'm going to tell you guys right now, pretty much all the problems I've picked pass the horizontal line test. But if you skip this part, you're going to probably mess up a problem or two just because you're skipping the check. You cannot skip your check. So 8 minus x cubed. Oh, there's some good stuff happening. All right, so we have a cubic function is dropping down from left to right, and it does seem to pass the horizontal line test. So when we come over here, it does pass the horizontal line test, and the range, if you were looking at it, was negative infinity to positive infinity, which means we won't have any restrictions on our domain later on. So let's switch this up. Y equal to 8 minus x cubed. Alright, so if you want to solve for this, there's several different ways to solve for this. But we'll just get y minus 8 equal to negative x cubed. And then we'll divide by negative 1. So negative y plus 8 equal to x cubed. And then we take the cube root, negative y plus 8 equal to x. And what you're going to begin to notice is if you do the problem differently, there are a lot of equivalent functions that make up the inverse. They're all equivalent. I think another one for this that comes to the top of my mind is the cube or the negative cube root of y minus 8. That one makes sense to me. That also gets us x. Again, going back to your function notation, the inverse of g of x is equal to the cube root of negative x plus 8. And we have no restrictions on our domain. Alright, so that pretty much covers all of the algebraic examples. You might run into a problem that looks completely different. I've given you some very different examples, some easy problems, some hard problems. I want you really to go check the assignment and see, like, can you do all types of these, because this is just a few examples, and you really need to get the good practice in before you can say you're a pro. So I want you to give these problems a try. Solve for g of x, f of x, h of x, k of x. Do not forget your horizontal line test. Alright, here are all the answers worked out. Some stuff you really have to think about when you look at these problems, but all the algebra is the same that you learned in Algebra 1 and Algebra 2. They really get applied at all the same time in pre-calculus because you see these types of problems come up, all these types of functions and models that you just got to work on. So the big thing is don't forget the domain restrictions. You all can start these problems. So let's move on. And let's determine if f of x and g of x are inverse functions. So kind of flipping the switch, we're going to confirm, is g of x the inverse of f, and vice versa, is f the inverse of g. So if I were to solve for f of x here, would I get g of x as my inverse function? So you can't get this from the graph. You cannot get this from the table. You can't just look at those individually and be like, oh, look, they're the same. Or they're symmetrical across the line y equal to x. That's not good enough. What you have to do is do f of g of x, our composition that we just learned. So we're going to get 6 over x plus 4 and then minus 4. Well, what happens here? We're going to get 6 over x. And then don't forget you have to flip and multiply. Multiply by the reciprocal. So now those 6's divide out and we get x. Yeah, you should probably look for some sort of pattern, especially when we do g of f of x. When we do g of f of x, we're going to get 6 over x minus 4 plus 4. Well, then we're going to say 6 and multiply by the reciprocal, x minus 4 over 6. The 6's divide out. Oh, I forgot the plus 4. The 6's divide out equals x minus 4 plus 4, which equals x. So when both compositions come out to say x, and it has to say x, they can't both say x plus 1, or they can't both say x squared, or one say x, the other one say negative x. They have to be the exact same. When that happens, you confirm they are inverse. But you have to show all of that. If you don't show all of that, then it's not good enough. Alright, I have a couple more problems. Go ahead, try these two compositions on your own. Determine if the following pair of functions are in fact inverse of each other. Oh, right. I know it's a lot of work, especially the second one with all the rational expressions and the complex fractions everywhere. But they both determine that we do have inverse functions on each. So if you got that, great. This actually concludes the lesson, determining if they are and verifying if they are inverse functions. But go ahead, try these problems out. And then when you finish those, try this challenge problem. Really use the definition to determine if how you're going to find the value of a. Don't forget, my name is Mr. Hernandez. You just learned about inverse functions, and I'm always here to help.